Hello everybody, today we will be talking about these two limits that were supposed to be back in chapter 2, but unfortunately it was kind of skipped around, so then it's basically my mistake. I kind of dropped the ball on as to like when I was supposed to introduce it. But nonetheless, here they are, and hopefully you guys can forgive me for that one. I want to talk about why is it that the limit as x approaches towards 0 for sine of x over x is equal to 1, and in addition to that, the other one, which is the limit as x approaches towards 0 for cosine of x minus 1 divided by x is equal to 0. Now, both of these limits you might want to consider memorizing because they do come up quite often, and so you will see them and they will be used quite often for the problems too. Now, let's go ahead and look at it using a graphical approach so you can see why it's true, and then afterward we'll go ahead and prove it by algebra. So if we go to Desmos over here, and that's Zoom, that's not Desmos, you can see I graphed both of the equation. The blue one is supposed to be the sine of x over x, and as it goes 0, as x goes to 0, you can see that it's getting closer and closer to 1, and you can't quite see the removable discontinuity there, but it's definitely there. Then for the red graph, that is the cosine of x minus 1 divided by x, and as x gets closer and closer to 0, you can see that it's going to the pole, which is 0, 0, so that's why it's going to be equal to 0 in that case then. So that's going to be looking at it from a graphical perspective. Now let's go ahead and prove them so you can see why does it work algebraically. So here underneath, what I did was I drew 3 triangles that are all congruent to each other. So you can see that they have the same height, the same base, and then the same ratio in terms of angles and sides. Now on the far left, what I would like to do is I would like to solve for the area of this entire triangle that's over here. So if you're looking at the area of a triangle, then you're looking at just plain old base times height. So that means the area, let me go ahead and change that a little bit. Let me erase this guy over here. Okay, so the area is going to be equal to 1/2 multiplied by the base, which is 1, multiplied by the height, which is equal to h. Now in the second triangle, what I'm going to do is I'm going to take the same triangle, but this time I am not going to find the area of the entire triangle, but rather I am going to find the area of this wedge right here that's created when you look at this as kind of like a piece of a circle. So you can see that little perforated part, that is supposed to be the circumference of the circle. So imagine if you take that radius of 1 on the bottom and you rotate it, that is basically a piece of the circle that I'm talking about. Now, since that part is supposed to represent the area of a circle, a piece of the circle, then one might say that its area is equal to pi r squared, right? Because that's the area of a circle, multiplied by the proportionality of the circle that you want. Well, the proportionality is determined by the angle that you can see over here, and it's going to be divided by what is 100% then. So what is the ratio? That's going to be x, and then divided by what is 100% of the circle? Well, that's the same thing as saying 2 pi radians. So that would then be divided by 2 pi. Finally, for the last part, I am going to take that circular wedge and I am going to divide it even more into a triangle, so that's a little bit smaller. So now you can see that we have introduced this red line over here, so you can see what is the area that I'm looking for. And just to kind of draw that out for you, the area that I'm referring to is everything that is in here all the way to everything that is in here. Okay, so that's the area of the triangle that I am referencing to. Okay, for any area of a triangle, again, we're going to need base times height. So that means that we need to kind of work around with this a little bit. So the one thing that we have kind of like not looked at, but we definitely should, is that remember that this piece right here, this arc, that is supposed to be the piece of a circle. So what that means is this length right here, that is also the radius, which is equal to 1. And that is actually very helpful because when it comes to finding the height, which is going to be located right here, you can see that that means we're going to use a certain proportionality. The opposite over the hypotenuse, so I'm looking at sine, so therefore the question mark should be equal to the sine of x because that's the opposite over the hypotenuse. And knowing that that is going to be my height of that triangle, then now put it all together, the area of the small little triangle that I want is going to be equal to 1/2 multiplied by the base, which is 1, multiplied by the height, which is going to be sine of x. Okay, let's go ahead and put all those three together. In terms of analytic geometry, if you look at the picture, one would say that the areas, in terms of like how they're related to each other, is that one is always going to be bigger than the other. Let's see, I would probably write it as the following then. The farthest left is definitely going to be greater than the next one, and the middle. And then the middle is going to be greater than the area of the bottom one. And in a case of where x is equal to 0, right? In a case of where x is equal to 0, one could even say that they're equal to each other, if that's even possible, because then they all have an area of 0. So then I can go ahead and write the inequality down here as well. Okay, let's go ahead and take all those three and clean it up together. Notice that they all have a 1/2 in common. So let me go ahead and kind of write it out so you can see it a little bit better. So h divided by 2 is greater than or equal to, let's see, in the middle, I have a 1/2, I have an x, and it looks like the pi's are going to cancel out. And yeah, I think that's it, right? That's just going to be x over 2 in this case. And then the far right, in terms of its area, that is going to be the sine of x divided by 2, okay? Since every single one of them have a 2 in the denominator, why don't I go ahead and multiply everything out by 2? So now we can have the following. Let's see. Oh, actually, hold on. I kind of messed up over here. The height over here, right? We can actually figure out what h is, okay? We can actually figure out what h is. H is supposed to be equal to the tangent of x because it's the opposite over the adjacent. So let me go ahead and kind of make that replacement. So here, my final equation so far, or final inequality, is that we have the tangent of x is greater than or equal to x is greater than or equal to the sine of x. Now focus on what is it that we're trying to build, which is going to be this guy right here, the sine of x over x. So what I'm going to do is I am going to go ahead and divide everything by sine of x. And if it helps you, tangent, let's go ahead and write it as sine of x over the cosine of x so you can see what happens there. So take this inequality, divide by the sine of x. And I can divide by the sine of x because since we're in quadrant 1, sine is going to be positive, so I don't have to worry about the inequality being changed. So now I have 1 over the cosine of x is less than or equal to x over the sine of x, and then is less than or equal to 1. And I'm going to do one last algebra trick to kind of change everything that I need. Note the middle is basically what I'm kind of looking for, but instead it's the reciprocal. So I'm going to go ahead and flip it then as a last step. So sine of x over x, the reciprocal of 1 is still 1. The reciprocal of 1 over cosine, well, that's cosine. And if you recall, when it comes to inequality, if you take the reciprocal of everything, then that means that the inequality is going to change. So making it so that it's going to be strictly less than or equal to for each one of these. Now, here's the last magic trick. We're going to go ahead and apply the limit for each one of these. Limit as x approaches towards 0, because that's what I want to solve for the middle. And see where that all is going to take us. So applying the limit now, we can see that the limit as x approaches towards 0 for cosine is strictly 1. The limit as x approaches towards 0 for sine of x over x is what we're trying to solve for. So then that means that we don't really care about that one. We'll go ahead and leave it alone. And then finally, the limit as x approaches towards 0 for 1, well, that's just 1 because there's no x then. And if we put it all together, you can see now the limit as x approaches towards 0 of sine of x divided by x is then equal to 1. So there's your proof done. Okay, take that right there. We can now use it to prove what I want right here on the other side, which is limit as x approaches towards 0 for cosine of x minus 1 divided by x. As a starting point, what I usually do is when I look at these problems, I'm thinking of like an identity. I'm trying to find ways to introduce something that I'm familiar with, and that's sine of x over x. So the best thing I can think of is let's go ahead and multiply by the conjugate. So cosine of x plus 1 on the top, cosine of x plus 1 on the bottom. And the reason for that is then you're going to get cosine squared minus 1 on the top, which then can be replaced by an identity. Okay, so that's how I'm going to sneak in the sign that I want. So limit as x approaches towards 0. The top is the difference of square, which is cosine squared x minus 1, divided by x times the cosine of x plus 1. Okay, keeping in mind that the top part, that is an identity, well, kind of an identity. It says that we have sine squared plus cosine squared is equal to 1. So if we were to kind of work our way around it, then cosine squared minus 1 would then be equal to the negative sine squared. So then that's what I'm going to have in here then. Limit as x approaches towards 0. And then we're going to have negative sine squared x divided by x times the cosine of x plus 1. And here is now we're going to sneak everything in. We're going to take that fraction and break it up into parts so we can see the limits. The first one will be the sine of x over the x that I wanted. The second part is going to be the residual part, which is the sine of x divided by cosine of x plus 1. And I'm going to go ahead and take that negative on the outside just so that you don't have to worry about it. Well, limit law says I can now break it into two parts so long as their limits actually exist and it's a finite number. So this is what you're supposed to get out of it. And now we can go ahead and see what each one of these are going to give me. This guy, we know that that's equal to 1, so I'm going to put that in there. Then this guy right here, this is going to be using a direct substitution because we literally can go ahead and let x equal 0. And if we do so, we're going to get 0 on the top because sine of 0 is equal to 0, divided by cosine of 0, that's equal to 1. So that's 1 plus 1 on the bottom. So negative 1 multiplied by 0. So the answer is equal to 0 then. So from here on out, you can go ahead and use these as kind of like identities slash theorems to help you with your proof. Let's take a look at a few examples. And then afterwards, I think that will be it then. So here's the first one. Limit as x approaches towards 0 for sine of 3x divided by 10x. What I want to do is find out what the limit is and according to what we just did. Now, there are two ways of doing this. You can either go ahead and do the following, which, well, you get to decide which one you want. So in the first method, here's what I'm going to do. I'm going to go ahead and say let u equal to 3x, which is basically the inside argument of sine. Okay. If I do so, then I'm going to get the following then. Limit as, and I'm going to go ahead and change everything in terms of u. So limit as u is approaching towards. Now, if x is approaching towards 0, then according to my substitution, u should be approaching towards 0 as well. The top part would then read sine of u. The bottom part, we have to figure out what's this replacement over here. So since u is equal to 3x, then that means that u divided by 3 is equal to x. So x times 10 is equal to 10/3 of u. So that would then be my replacement that's on the bottom over here. Hey, looking at what we have, if you look closely enough, you'll see that this is the part that we're really looking for. Limit as u approaches towards 0 of sine of u over u. That, as we said, is equal to 1. So then that means my answer should be 1 over 10/3. And the reciprocal of that, that's going to be my answer, which is going to be 3/10. So that's one method of doing it. Now, an alternative method is the following. Limit as x approaches towards 0, and then we have sine of 3x divided by. Now, here's what we'll do. I want the bottom to match the top's composite function. So what I'm trying to say is I would love to have a 3x that's on the bottom over here because then I can see that that right there is equal to 1. Now, in order to balance the equation out, then that means that I need to multiply 3x to the top over here as well. Well, this right here hopefully is a little bit clearer as to what it's going to be. Since this right here is going to be the same thing, even though over here it says x, well, I mean, if x is going to 0, 3x is definitely going to 0 as well. So that means that this part is equal to 1. And with whatever's left over, you can see the x is going to cancel out. So 3/10 is going to be your answer. So yeah, exactly the same thing. So you pick whichever method is best for you then. Now, let's take a look at the second problem. Over here, same idea. Let's say this time we have limit as x approaches towards 0 of tangent of 5x divided by sine of 4x. When I look at this problem, again, I want to change everything to sine and cosine. So in that way, we can see how to actually match things up. So first, let me go ahead and rewrite this. So limit as x approaches towards 0. I have sine of 5x on the top, and then we have cosine of 5x on the bottom, and then we also have 1 over sine of 4x that's over there. Okay. Now, if you like this method over here of what I did on the right, let's go ahead and go by that because I think we have something to work with. Okay, so here's what I'll do. I'm going to take everything that has sine, right, and input the place, input something that is going to allow me to get that limit of 1. So over here with a sine of 5x, I'm going to go ahead and divide by 5x, okay? Then, if you notice that we have the sine of 4x, I am going to put at the top 4x to match up with the 4x that's down there. With what's left, I need to basically balance the equation. I still have the cosine of 5x. And don't worry about multiplying 5x to the top and bottom because there's nothing with cosine of x divided by x. So that part you could just leave. But what we do need to consider is what we multiply to each respective numerator and denominator, we have to cancel it out. So that is to say, I need a 5x on the top, and then I need a 4x on the bottom. Okay. So now that we have all of this, we can kind of clear things out and just see what happens then. So this part and the first part, you can see that that limit is going to be 1 because the components are going to be the same thing. This guy over here, that's also going to be equal to 1 because there's a limit law that says that if you take the limit of something and then you raise it to some power, it's the same thing as the answer raised to the power instead. Basically, this is what it says. If you have the limit as x approaches towards a of f of x, and this is going to be raised to the h power, like this, then that is going to be equal to the limit as x approaches towards a of f of x, and then you find that answer raised to the h power. So in this case, h is equal to -1 because it's just a reciprocal of it. Finally, for this last part over here, we can see that the x's are going to cancel out, so that's nice. And x, I can literally let equal to 0 because that's not going to be a part that's problematic because cosine, well, cosine of 0 is equal to 1. So all we have left is 5/4, and that's going to be our answer then. Okay. Final part right here. Limit as x approaches towards 0 of cosine of x minus 1 divided by sine of x. If you notice what we have right here, this is actually a very simple problem because it's just one simple trick. It looks literally just like both of the limits that I actually have. The only thing that's missing is the x on the bottom for each one of these. So what I'm trying to tell you is let's go ahead and introduce it just like we did in the previous problems. So limit as x approaches towards 0 of cosine of x minus 1. Here's one fraction, sine of x on the bottom, the other fraction. Let's go ahead and multiply x to the top, x to the bottom to balance the equation. Now that we have every piece that we need, then we can say that this can now be split into two parts. Limit as x approaches towards 0 of cosine of x minus 1 divided by x times the limit as x approaches towards 0 of x divided by sine of x, right? And this one, I'm not going to skip any steps because then you can see what I was talking about in the previous one. This guy, that definitely goes to 0, so that's easy. Now this guy over here, if it helps, let's rewrite it. Limit as x approaches towards 0 of sine of x divided by x. And all that is raised to the -1. Right? As I was saying, I'm going to take the reciprocal of it and whatever the limit is, take the reciprocal of it again, just to kind of balance out the equation. So 0 times 1 raised to the -1.